All right, stand up for me real fast. Real fast. And I need you to, okay, so you gotta listen up, okay? So find somebody across the room, be with them. Like, walk through them and stand next to them now. Don't knock glass off the desk. All right, and stand next to this person, or maybe you're next to a couple people, you're nearby. Right, I have a big clump, so spread out a big clump. Your clump is too much. Okay, so I want you to tell them the 3 nuclear decay particles you learned about. Go. All right, pause. I heard alpha, beta, gamma. I want you to tell them the most, like, violent, the most penetrating one. I hear questionable comments. It is gamma. Okay. I want you to tell them about what is fission versus fusion. And go back to your seats. Thank you. All right, so halfway shut your laptop with me. You don't have to close it all the way. If you need to reference a slide again, you absolutely can. My slides are going to be up here. I'm just going to hit the highlights of what I feel like I need to elaborate on, and then show you how to problem solve some of those equations, and then half-life. That's my job today, okay? Who's a little bit familiar with nuclear chemistry? Maybe you've heard of it in real life. Where is it applicable in real life? Nuclear bombs. Keep going. Nuclear power plants, which is our preferred method to use it for. Particle accelerator in Switzerland, where they collide particles and they make new atoms. That's how they made all that crap on the end over there that was whatever until we created them. Where else?
Big Bang Theory.
Big Bang Theory. What's this thing? Where's that? The smoke detector. It's like right there. You guys know what's in there? Okay, smoke detector. It can be around the fire alarm, actually. They're combined because it's going to detect the smoke for the fire. Okay? All right, so what's in there that's maybe radioactive? Does anybody know? Fun fact of the day, americium. Americium, which is an element symbolized by what symbol? Take a guess, guys. AM, right? Americium was discovered in America, right? Americium, it was once called. Basically, as it is radioactively decaying, and as smoke is pulled into the sensor, it blocks the action of radioactive decay, and then it sets the fire alarm off. Okay, so we use it for that. Who's ever eaten a banana? Right? Most of us probably at some point in time. Bananas are, the potassium in the bananas is radioactive, but it's so slowly decaying, we don't really consider it too harmful to us. Okay, so we actually interact with radioactive decay every single day in some way or form, but some of it's really harmful and some of it's not harmful. Most of us are still doing okay right now. Insides aren't falling out and stuff, so we obviously haven't been too exposed. But if you've ever seen a nurse like who works with x-rays, they have like a little badge on. You know what that badge detects? Radiation. If they're overexposed to radiation from too many x-rays, or they're on call too much whenever the x-rays are being done in the room, they have to send them home with pay, because they cannot be overexposed in a given month, because that's obviously harmful to their well-being. So my sister wears one. She works in pediatric hospitals a lot, so she used to wear one, and if they have to watch how much radiation you're exposed to. So you have that to look forward to if you're going to medical field. Okay, so here we go. We might know a little bit about this. Hold on, let me go to the slide that matters. Okay, so this was a big slide that you wrote down. Alpha, beta, gamma are 3 particles. What we should know is that there are 2 or 3 ways to really, 2 ways to denote everything here. So helium is really what an alpha particle is, what it looks like, because what's inside of an alpha particle? What's the 2 refer to? 2 protons, right? So 2 meaning 2 protons. And then what's the 4 refer to? Mass, which also includes what? 2 neutrons, right? So 2 protons plus 2 neutrons equals 4. Everybody, what's the mass of helium? 4. Okay. Now that's one symbol for is He, helium. The other symbol is the alpha symbol. fish. Looks like a fish, right? But it's symbolized by the same mass and proton count. So that's a pretty massive particle compared to the rest of these. So it's a big chunky particle. It's called alpha particle. Then we have the beta particle, which, how much does it weigh? How much does it weigh? Zero mass. What's weird about this is that we can, well, first let me tell you the symbols. Okay, so 0 is the mass, and what's the proton count? -1, which you can't have negative mass, right? Negative proton. So essentially what's happening is, we're talking about the nucleus, right? What's in the nucleus? Protons and neutrons. Normally I would tell you never, ever, ever to change the proton count, because the proton count represents the atom, right? So if I change the proton, what do I change? The element type, right? So, but since we're talking about nuclear chemistry, we're talking about nuclear decay, this is the only incident where we can ever change the nucleus's composition. So with the beta particle, what happens is it takes a proton and it changes it into an electron, and it pops it out of the nucleus. So it takes a what? Proton, and it changes it to an electron, and what happens to the electron? Pops out of the nucleus. So that's why it has a -1 charge, or -1 proton number, because it's actually swiping away one proton as it transmutates it into an electron. It's a very weird circumstance. But we label it as B with a tail, like a long tail like that. That's a beta particle. And also, as you can see over here, E. Why do you think they use the symbol E? Because it essentially is an electron. It's a highly energetic electron. And I asked for you guys to leave some space so you guys can annotate and abbreviate this add to where you need to. Because I'm talking a lot, I'm writing some things down, I would abbreviate, or add on to your abbreviations. And then gamma really only has one designation. It's a big upside down Y fish. What's the mass? 0. What's the charge? This baby is straight up energy. And we already knew that because we've heard of the electromagnetic spectrum, and what's on the far short wavelength end of the electromagnetic spectrum? Gamma rays, right after X-rays and so forth. So it's just straight up energy. It doesn't have any mass. It's just like, if you're the nucleus, what's inside again? Protons and neutrons. Now, what if two protons get kind of close together? What do they start to do? Repel, right? Plus and plus, they start to repel. So what happens is if you have too many protons in your nucleus or too many neutrons in your nucleus, you're just not stable, meaning you're radioactive, you're unstable. So you're going to break your nucleus down until you get to a stable format. Sometimes it just takes a little wiggle, like the protons just kind of wiggle and they move away from each other. But when it does that, it stabilizes the nucleus, and then it goes, and it releases a little bit of energy. And guess what that energy is? Gamma radiation. Okay. Sometimes it's just the nucleus rearranges itself. It doesn't really emit or eject anything. Like it doesn't eject an alpha particle or beta particle. It just rearranges itself a little bit and ejects some energy. But that's pretty dang harmful energy, so we try not to get near. But here's what you can do to protect yourself from nuclear particles. 1, hold up the thing that can block an alpha particle. Okay, block by alpha particles. Alright, so you've protected yourself well with paper or clothing. Alpha particles, if you swallow them, they bounce around your insides and kind of starts to destroy little pieces of tissue, but your body does a pretty good job of neutralizing that threat. What would block a beta particle? Like it says metal foils. Give me an example. Aluminum foil, tin foil, copper foil, any kind of foil. So I'm trying to indicate to you what's a more what's a more harmful particle. Who's more harmful? Who's more penetrating? Beta. Because beta, it can come through paper, it can come through clothing, but it can be blocked by metals, which is they're a little bit more substantial, right? So it goes in order of like danger. So in order of penetrating power. Alpha particle, you put your clothes up, blocks. But beta particle, you put some clothes up and it goes straight through, goes to your skin, to your body. Gamma, on the other hand, unless you're walking around in a lead suit, you're not going to block yourself from gamma radiation. What you would have to do is have a concrete wall and live in a 6-foot concrete wall room, or have some lead vest on. So we've maybe done that once or twice in our life. When have we worn a lead vest? X-rays, right? Dental X-rays. Or if you're doing like a X-ray of your knee and they don't want any gamma radiation getting to your internal organs, they put a big vest over you so they can just X-ray that one part that needs some sort of visualization. So we've encountered that before because gamma radiation, which can be coming off of X-rays, are pretty harmful. Got it? So who has a mass of 4? And who has no mass? Gamma and beta. Who is consisting of 2 protons? Who's consisting of 2 neutrons? Alpha. Okay. Easy multiple choice questions to get right or wrong. But let's get them right, okay? All right, so the next one was the system of how we show the nucleus decaying. So we actually have to show the A to Z notation on how these things are decaying. This is the first one, right, on slide 9? Just verify that for me. Okay, so here we go. I'm going to show you how to do this and then show you the process, and then I'm going to try to let you guys do the rest. So we have carbon 14, C14. We're going to write it like a true reaction, like reactants yield products. Okay, so this is the reactant, and what's the Z number for carbon? How do you know? Periodic table says it's 6, right? That's all we have to do. I won't tell it to you because you always have your BFF, your PTOE with you, so you should know it. All right, so that's our complete reactant. It's undergoing beta decay, so I'm going to let it decay, so yields a beta particle. So, Chris, what's the symbol for beta particle?
Capital B.
Okay. And then the numbers for it?
It's 0 and -1.
Okay. And here we go. So essentially, the mass, like law of conservation of mass, law of conservation of matter, the mass should be the same from reactants to products as should the bottom numbers down here. Because we're not really destroying protons, we're making them look different. They're looking like electrons now. So I'm going to decide on what I'm going to add here to balance this out. So 14 is equal to 0 plus what? 14, okay. Easy math. That's a 1-4. My pen likes to get off basically every day, guys. Sorry. Okay, that's 1-4. And then 6 is equal to a -1 plus 7. Good. Nobody said 5. All right, we're doing good. All right, so I have transmutated, I have radioactively decayed carbon 14 into this particle, which is who? How do you know? Atomic number 7, right? All right, and that is who we transmutated or radioactively decayed carbon 14 into. So carbon 14 is something that we use in radioactive dating. You've heard of this, like dinosaur fossils. Like we actually use this. So what they're looking for is, you know, at some point in time, they're going to find a detectable amount of nitrogen 14. And so they look to see how much nitrogen 14 is there compared to how much carbon 14 is there, and then they give an estimate of the age based on that. So that's actually the reaction they utilize. All right, next one. Can you guys do B and C? You might need your periodic table unless you have like super hot moving. If you can keep going, keep going. I'm just going to interrupt you in a second so I can check those first two with you. All right, let's check B together, okay? Aiden, help me with B. I got B, so boron 8. What's the atomic number for boron? 5, okay. It's undergoing beta decay, so we're decaying this. Moving on.
So it's B with a tail and then.
Can I change? I'm going to just modify it. So we did B with the tail, the beta particle map method on A. Let's try it showing off a different representation. Let's do E. 0 and what? -1. Okay, so what's going to be completing my mass here?
So you'll have 8 and 6.
Okay, how did you get 6 here?
Because you have to add 6 to -1 to get 5.
Right, so 6 essentially -1 is equal to 5. The yield symbol acts like an equal. And then who is this?
Carbon.
Carbon, right. So boron, it sounds weird because boron's to the left of carbon, but boron 8 is decaying to carbon 8. Which is weird because it's 8, but that's what it is. Okay, let's do the next one. Kendall, get me started on C. the Z number is what?
53.
53. Okay. All right, hold on 1 second. So give me a thumbs up if you've accomplished C. All right, go ahead and finish that up real fast before we move on. If you're moving ahead, you keep moving ahead, okay? All right, Kendall, I'm ready for you now. So iodine, mass of 125, 53 is atomic number. You pulled that from where? Periodic table. Okay, so it's decaying and it's forming a what?
Alpha.
So tell me what I'm writing here.
4.
Okay? Okay, so we're going to do the A fish thing. Or instead of writing A fish, we could write HE for helium, right? Okay, keep going, Kendall.
If you add 1.5, 4.
No, 125 is equal to 4 plus what? Do the math with me. 121, okay? So essentially, the product numbers add together to equal the reactant numbers. So 4 and 121 equals 125. Do the bottom for me, Kendall. 51, okay? So 51 plus 2 is equal to 53. Think of the yield symbol as an equal symbol. And who is tell me 151? Who is it? Cesium? SB, right? You're going back. Go back. Yeah, because I was like, we can't go forward, you're going to go back. So antimony, or SB is antimony. Okay, so iodine 125 decays through alpha particle decay to form antimony 121. So far, have we been showing fission reactions or fusion reactions? Loud and proud? Fission, because fission takes one thing that's kind of big and unstable, and it does what? Splits it into like kind of a small particle, which is the K particle, and then one larger nuclide, which is in this case antimony. So everything so far has been fission, fission, fission. All right, CJ, get me started on D. And you got that from? Okay, keep going. And will you give me the other notation here? Okay, so this is an alpha particle, this is an alpha particle, same thing. Keep going. Polonium. Okay, so 4 and 206 is equal to 210, good. 2 and 84 is equal to 286, good. And then 84 is the atomic number of polonium. And so we had another alpha decay. Last one, let's do this one together. We have nickel 56. All right, everybody, what's nickel's atomic number? 28. Okay, so there's 28 protons with some neutrons in that nucleus, right? So it's undergoing gamma ray decay or gamma ray emission. So give me the gamma ray. 0, 0, and Y of something, right? Okay. And then what's it form? It stays nickel, right? 56 and 28. So why did this happen? Well, no, but why would this undergo gamma ray emission or gamma ray decay? I just mentioned this. I don't know why. So why is this unstable? I mentioned like one scenario. Well, so we're not changing the protons, right? So the protons are staying the same. So I wouldn't say there's too many, but what did I say about those protons? Do you remember? Right, if they're kind of arranged kind of too close together, or the neutrons are too close together, they just kind of rearrange the nucleus just a hot second, and in that process it just relays a little bit of energy out, which is the gamma radiation, and then now this nucleus is more stable. In this case, nothing really changed, but it did change the internal arrangement. Are we okay with that? So these are called nuclear decay equations. Nuclear decay equations, and so far all of these were written how? Fission or fusion? Fission. So fusion, doesn't it just sound like it goes together, like things are fusing together? Like you take two big things and you push them together. All right, so are we okay on nuclear so far? Yes. Okay. So that's the penetrating power. Okay, great. You guys wrote down most of this. We know that. I only had like two things I wanted to show you guys. Oh, and then radioactive half-life. Yep. And This one's interesting. So this is called a decay series because sometimes, like here's thorium-232, it undergoes alpha. You see the alpha particle there? Alpha decay, and it forms radon-228, and then that undergoes beta decay, and then that undergoes beta decay, and then that undergoes alpha decay, and then alpha decay, and then alpha decay, and so there's a series, it's a chain reaction. Sometimes it doesn't just stop at one, there's a decay chain until it finally hits something that is stable. So essentially what it's showing you is that all of these are unstable to some extent, and who's the most stable of them all? Polonium-216, right? Because it has stopped decaying because the nucleus is now in a happy place. So that's called a decay chain. So that's one fact you should know. And then transmutation is the other word I was using. What can I exchange transmutation with? Say again? Well, no. I was saying transmutation, and I was interchanging that word with something else just now. It's when you change an atom from one type into another. So what's the big thing for the day? Nuclear decay. That's it. Just radioactive decay. All radioactive decay generally changes one atom into another type. So another word for radioactive decay is transmutation. It's just mutating. What's mutation mean? To change. That's it. So transmutation means it's to change the nucleus. Okay. Oh, and then Bryce, tell us about the particle accelerator.
It's in Switzerland.
It is in Switzerland. Can you give me more?
It like makes particles go really fast, and then they smash together, and then they examine the inside of the particle.
And they look to see if they've made something new. Right. So this is like supposed to be a computer graphic of this, but essentially there's I'm going to say like a 6-mile atom racetrack underneath Switzerland. And so they'll throw one atom going counterclockwise and the other atom going clockwise, and they're hoping that they'll collide. So they're called atom smashers because they're smashing atoms together. And they hope when they do that, they fuse the nuclei. So they're hoping that they can take something that's protons of 80 and adding it to something that's small, like maybe they wouldn't want to go bigger. They want to go past 114 because everybody's trying to make a new element to get their name on the periodic table. So essentially, atom smashing is supposed to make a bigger nucleus that stays. It's got to be stable. And once they make that, they have claimed that made a new element. So all this extra time scientists have, right? Yeah.
What would happen if they made like enough to where it like fills that unknown?
We had to trash all the textbooks and just make another row. No, I mean, this is what we've discovered so far, but theoretically, there's, unlimited number of more we could make if we were good enough with our science, which right now we're doing okay. But there also might be other things on other planets that we are not, they're just not stable in this atmosphere, so they're not found on planet Earth. Dun dun dun. Okay, fission and fusion. I think you guys got this. Big things break, small things fuse. I'm keeping it simple, okay? And then you might want to write down the examples with the fusion. A good example would be what? Fusion. Fusion. The sun. Okay, who read that sun article? Okay, so you should be able to talk a little bit about that. And then fission, a good example would be nuclear energy being produced from nuclear power. Very good. So there's the Springfield. Okay. Yep, another picture of that. Good job. Lots of pictures. Okay, so radioactive decay. So let's learn how to do this one. Who has taken math 2 or 3? Have you guys done radioactive decay? Math, is it math 3?
Well, we did like a
You did have. I mean, that's what this is.
Yeah.
Was that math 2 or 3? 3. Okay. So I remember Miss Hayes was asking me about like, does it ever go to 0? It doesn't, but yes. Okay. Here we go. Here's how I can approach this really easy, and then we're going to do this in a little bit more of a math sense. You have carbon-14 emitting beta radiation, blah, blah, blah. It has a half-life of 5,730 years. Assume you start with this mass, how long is 3 half-lives, and then how much will be left after those 3 half-lives. So here we go. 1 half-life, and this is how I'd write down my information so that I can process the question. I'm not reading this thing again, okay? So the half-life is equal to 5,730 years. Okay? Write this down with me. And then the mass initial, mass with a little I means mass initial, is 2.00 times 10 to the negative 12 grams. Okay? And it wants to know how long is 3 half-lives and then how many grams of the original isotope is left final. So like mass final is what we're looking for. That's our question. Okay, easy peasy on getting me 3 half-lives. If 1 half-life is equal to 5,730 years, how do I get to the length of time 3 half-lives is? Multiply by 3. We can't make that any harder, right? So we're going to take this, say half-life times 3, which would be 5,730 years times 3. And what is that, guys? Huh? Calculators, pull out your phone calculator, get on the computer just so we can knock this out. Corbin? 17,190 years. Okay. So that is answer 1. That one's pretty easy to achieve. Okay, so 3 half-lives passed. Definition of half-life is how much time it takes for that sample of radioactive material to decay to what? Half the amount. So if I start with 10 grams, half of that amount would be 5 grams. If I start off with 100 grams, half that amount would be 50 grams. Just cutting the mass in half. So we don't actually have to use a calculator on this one. We're going to try to do this in our head. So if I start off with a mass of 2.00 times 10 to the negative 12 grams, after 1 half-life, how much should be left of this original isotope carbon-14? You don't have to math it. Cut it in half. Say again? 1.00 times 10 to the negative 12 grams. That's the original mass of carbon-14. After 1 half-life has passed, this is the amount of carbon-14 remaining here. After a second half-life has passed, how much should be left? So 0.5 times 10 to the negative 12, can you give that to me in appropriate scientific notation? 5 times 10 to the... Yeah, because it needs to get smaller, right? So negative 12 is small, but negative 13 is smaller. So it needs to get smaller if you're thinking about how do I get the exponent right. Okay, so that's 1 half-life passed, we cut it in half. A second half-life passed, we cut it in half. A third half-life passed, and then we cut it in half. What is that? 2.5 times 10 to the negative 13 grams. And this is mass final for carbon-14 after 3 half-lives is passed. Which, how long was 3 half-lives again? That many years, right? So that's how much would be left. Now, this is really simple because I already knew the half-life, so I just cut that baby in half 3 times. But what if I was like, all right, guys, 17,190 years have passed. The half-life time is 5,730. How much is left after this elapsed time? Sometimes it's a perfect number complex. Like, that's obvious because that's the same number, so it would be 3 half-lives passed. You could just cut it in half 3 times. Another way to approach it, though, would be like, it's related to PERT. When I say PERT, you know what I'm talking about? Yeah. Okay, so it's related to that, but we're going to modify a little bit, okay? So write this equation down. Mass final is equal to mass initial times parentheses 1/2 raised to the power of, I can say this in 2 ways, but I'm going to use the more complex version first. Elapsed time over half-life time. HL means half-life. So mass final is equal to mass initial times, oopsies, just trying to get some space here. Don't look at all this junk down here. This is more complicated than it needs to be. Okie dokie. All right, so let's say I didn't solve this problem. Let's try it out and see if it works out the same. What was mass initial? Okay, 2.00 times 10 to the negative 12. We're going to multiply that by 1/2 raised to the what power? Okay, so the elapsed time was what? 17,190? 190? Okay. And then the half-life time was 5,730. We know that is 3. Like, we know that. But let's say it was an awkward number and we didn't have the exact half-lives that passed. So if you now actually might want to grab a calculator, unless you can plug that in your phone appropriately. Try that out. This is proof of concept. Chandler is more than willing to pass out calculators if you're ready to do
Go ahead and do some manually.
Google is helpful. Just trying to see if it's the same number, guys. That's it. I'm just proving math works. That's all I want to do to you today. What? 2.5 times 10 to the what? Holy moly. Hot dog, that's the same number we just found. Now, if you were to have a more difficult problem where the half-lives were not a perfect integer, I would be using this equation. But if I had like 3 half-lives to go, I would just cut that thing in half 3 times because that's so much easier to do even in my head. So I gave you option A and option B. Pick your poison, okay? We okay with that? Okay. So that would be more multiple choice questions, mainly because I think that's too easy for you, so you work for okay, so go ahead and do this one for me. This will be the last one we do together. And again, pick your poison, easy math or intelligent math. I don't know what you want to do about it. All right, Bailey, how many half-lives have passed? Say again? How many half-lives have passed in our elapsed time? How could I figure that out if I wanted to? Say again? Okay, so I give you 10.4 hours divided by 2.6, and what do I get? All right, 4 half-lives. Now, we know this is going to be our easy route. Everybody, what's my initial mass of manganese 56? 1 milligram. Okay, so I'm taking the easy way first. Give me 1 half-life. 0.5 milligrams. Okay, give me the second half-life. And I know this sounds silly, but if you don't label them, you'll forget how many half-lives you passed, and you'll get the question wrong. Okay, so this is the second half-life. Goes down to what? 0.25 milligrams. Okay, the third half-life goes to what? So 1 to half to 0.25 to 0.125. You can do this in your head. So that's 3 half-lives. And last one? 0.0625. Good. Milligrams. Great. So that's pretty easy if you can think about having that number of times. Another way to approach it would be how, Ryan? Equation. So what would you plug in that equation?
1 times 1 half.
Times 1 half.
And then index. So you put this in parentheses too. 10.4.
Beautiful. So like I said, pick your poison and this will work out the same way. It'll be 0.0625 milligrams. All right, guys. Let's do a little bit of an activity here, okay? So get your nuclear chem reading back out. You didn't put it away at all. So that's your annotated reading. Can I get past this? Slide. Not quite. Okay, I'm going to leave it there for a second. Okay, so what we're going to do is we're going to just quickly, before you get back into our groups, we're going to practice active listening. So I used to do like collaborative group training with all my classes every year, and I'm kind of been peppering it in for you guys. So active listening means that you give eye contact with the person who's speaking. You're going to be smiling at them, and you're listening, and you're going to be like shaking your head and leaning forward, which is encouraging them to give you more information. Because if you're back like this, no one's going to want to talk to me. And I look so disinterested, don't I? frowning, arms crossed, like get out my personal space. So practice active listening or conversing with the person next to you. Go. All right, come back to me. Come back to me. That was just a quick practice. We're not sharing until we get into bigger groups, okay? So all of us had a different article, or we all had 3 articles total. So they're going to be groups. You guys are going to be groups of 3, which is all representative of an article. I need the sun folks to go stand in that corner. The chemical element formation in the back corner, and then the antimatter up here. Antimatter front corner. All right, and line up. Once you get there, line up. You guys can just line up right here. It's fine. Stand in a line. Got it, Clump? Okay. All right, first person, number off is 1, and then continue. I'm just going to get you guys to get a number. You guys got those numbers?
I'll be number 4. I'll be number 4. 4, 5, 6, 7, 8, 9, 10. Hey.
All right, everybody has a number.
Yeah.
All right, 1's guys, move come up here. Wait. 2, 3, 4, 5, 6, 7, 8, 9, 10. Go.
8. 4.
Now read the instructions on the board. Read the instructions on the board. You guys can group together and then
All right, let's go first.
I think I also have
We need paper, don't we? Alright, we'll just do that first.
instructions on the board. Start.
Can we do that wall? I guess we'll do the facts later. So, I had an argument. Basically, antimatter is identical to ordinary matter in like every way.
Unless you want to stand up, it doesn't matter to me. You're fine.
Get a pencil.
Just talk first. Just talk it out.
The first particle is discovered by Brown. Inside the sun is If your next person has now started sharing, second person should be sharing now. So base like this.
So basically, inside a sun, there's a bunch of helium. No, hydrogen. And then that fuses into helium because the pressure driven by the outside of the sun. And then gravity. There you go. That one. And then it basically just keeps using hydrogen keeps going until it gets higher. And the reason this works is because everything before on Earth continuously creates energy to repel the gravity. Because if it relies on itself, it doesn't create anything. So eventually it'll run out of something to use. And then it'll collapse in on itself called supernova. And the supernovas things
Alright, third person is sharing. Third person is not here.
Mine about the sun. We started off with how early cultures were obsessed with obsession throughout history. Mankind has created gods for it, etc. One in time they thought it was a important piece of coal. So we were pretty stupid in the past. And eventually, modern theories came around. We were disproved before that, where we have some nuclear service, and how, as you were saying, helium and hydrogen, the way it uses, creates energy for light. And then we ended up classifying it into different levels, categorizing like how we have levels in Earth. So they've broken down to the four outer layers of the chromosphere, and now some of them can only see during specific events, such as like solar eclipses.
Which I find that cool. I didn't know the sun was there. I thought it'd be way back.
One of them you can only see it gives off a heat. You can only see it during solar eclipses.
No, things that are dangerous to look at.
Yeah, and then it talks about how we can use the solar energy to heal our lives.
I think I actually looked at that video.
Alright, and 5, 4, 3, 2, 1. Okay, so I hope that you have now become a better person and more knowledgeable. What I want you to do is you're going to make sure your name's on that, and you're going to put this in the box in a second. And then when you get back to your desk, find the atoms being made. Go.
I hope we give this at the beginning of the year.
Beginning of this universe.
Is that okay for our summary and analysis thing on?
Yeah, your summary and analysis should either be on the sheet because there was extra space or stapled to it. Do not turn it in without the summary and reflection. If you do turn it in, if you do not have your summary and reflection done, I will turn it late tomorrow. It's going to be a 90, and without a summary and reflection, it's a 60. Got it? If you turn it in without a summary and reflection, it's a 60. That's tomorrow, it'll be a 90. So that's the better option.
We had it passed out for it.
Yeah, so very beginning of this unit, I passed out this. I know, I put a lot of responsibility on you guys keeping up this paper.
It's on the scavenger sheet.
Alright, so while you're rifling through papers, listen up for me, okay? Alright, so I'm a fan of making you guys good? Alright, so hold those conversations for a minute. I have a couple of extras if you slackers forgot them, so I got 4. So, I'm a fan of making you read chemistry, think chemistry, speak chemistry, interactive chemistry, dramatize chemistry, whatever I can get you to do, because the more ways you learn something, the more likely you are to be able to really thoroughly understand it. And one of the big pieces of, tell you guys about the 7 things, like 7 interactions, your brain remembers it more, right?
Yeah.
So the theory is, guys, you have a big process in the brain. If you read something, and now you try to remember what you read, That's 24 hours later, you've forgotten 80% of what you read. Okay? If you read something and then think about it, you remember a good 60, you remember like around 50%. If you read, think, speak, and teach something, you remember 90% of what you do. So what you're going to do is you're going to review, starting to review, via teaching something to somebody else. But it's not going to be very long, like it's not a lecture, it's not a lesson. It's going to be quick and fast, okay? So this is people bingo, all right? So the only way you can cross off one of the spots on your bingo board is to have someone else give you information about that concept, about that question. So I can go up to Chandler and say, okay, Nathan, I need you to give me the answer for A1. So that's going to be A1, which is describe Dalton's atomic theory, or atomic model atomic theory. So if he's like, I can't do that one, let's pick another one, he can take which one he wants to give me. But my goal as a strategic bingo player is I want to get either a full horizontal line, a full vertical line, or a diagonal line, right? Because that's how bingo works. So today I want you to have a interaction with at least 5 people or more, because those 5 people are going to give you 5 boxes that they can check off. So when Chandler answers my question, someone's like, yeah, okay, high five, and he's going to like put his initials on my A1. And then I can't just, it's got to be a mutualistic relationship, right? I can be like, peace, bye. He's going to be, Inlo, I need you to answer S5. What is the difference between nuclear fission and fusion? And so the minute I answer him, he says yes, and then I'm going to sign off on his. So if you scratch my back, I scratch yours, right? So you must be able to give an answer to somebody else after they give an answer to you. Does that make sense? Okay. You don't. They're going to put their initials there.
Oh,
Okay. So that's going to be how I can see when you have bingo. So that means that once you've answered that one person who's interacted with you, you're not going to see them again for the entire bingo session because they will have already done their good deed for you. Okay. So you're going to interact with probably every person in this room to get this whole thing done. Question? The show work one. Some of it's going to be written down here in the bottom. Question?
Don't have to write down your answer.
No, this is a verbal interaction, oral interaction, teaching interaction, yeah.
And we just had to fill up the bingo, right?
Yeah, so for today, I'm hoping we can get 1, and we're out and tomorrow. So if you get more than 1, absolutely, let's go for it, okay? And go. I'm not your person. Ask somebody else, okay? Ask somebody else.
Alright, so
and H is 6.26 times 10 to negative 34.
Yes! What? I'm sorry, I didn't hear the units. What did you say? The units? Right. Oh, he can help.
Right here. Let's go with the. What is that? Is that the M over S? Huh? That's what I was about to do. Oh.
It's not metals versus non-metals. Alright, so metals, right? You got these cars shining, those things, right? So the electricity, the current, it's just too easy for metals, for non-metals, they're really brittle, are easy to break, and they're hard to melt. And they not, like, electricity, it's just,
Alkaline metals, barrier motion, we only have one down.
Ion? I don't even know how to explain that to you. Okay, so when you go up, higher, and then why? I'll call.
Alright, listen, 3, 2, 1. Raise your hand if you have a, guys in the back. Raise your hand if you have a bingo. different atoms. Okay, raise your hand if you have 2 bingos. All right, let's see if we can get 2. Go. Spread out if you're at the back station. You can't talk to anybody who's like 18 deep. Let's go, spread out.